Okay, hello everyone. I think it's time. So again, welcome you all to 2021-22 first semester lecture series. As you can see from here, that we will firstly, for this year's lecture series, we will firstly discuss about basic knowledge regarding medical physics and radiopharmaceutical development in nuclear medicine. And then we will move on to clinical application of nuclear medicine with advisory from Professor Edmund Kim. And today's subject will be nuclear medicine physics. And I'd like to introduce today's lecturer, Dr. Jae-sung Lee. Dr. Lee, you will well know from the previous workshops and lecture series. He is currently the professor in the Department of Nuclear Medicine, Seoul National University Hospital, and he has dedicated to many research and clinical application of nuclear physics, from the development of PET machine softwares and application of AI to the nuclear medicine. So today, Dr. Lee will deliver us a lecture regarding medical physics basics. And so please welcome Dr. Jae-sung Lee.
Can you hear me?
네, 잘 들립니다.
네. So thank you, Professor Seo, for your kind introduction. Let me share my screen. 잘 보이시나요?
네, 잘 보입니다. 네, 잘 보입니다.
Okay. Okay, good morning, good afternoon, everyone. So it is very nice to meet you again. It is also my great honor to give you my lectures on basic physics today. Actually, you know, the Professor Seo asked me to provide, some, the very basic, the lectures on the nuclear medicine physics. So I was wondering, so what kind of information that I can, provide you, because, that there are a very wide range of, the medical physics that, should be known for, nuclear medicine. So because of the, the time limitation, I have decided to focus on the basic physics, related with the, radiation measurement. So today I'm gonna talk about the interaction of, radiation with matter. So that is, very basic knowledge to understand, how we can measure the radiation using the radiation detectors. And next time, let me, introduce you, basic the principles and mechanism of, radiation detectors that used in nuclear medicine. So based on the lecture that I will, give you today on the interaction of radiation with matter. Okay. Actually, the main contents of this lecture came from the textbook, Physics in Nuclear Medicine, the famous, textbook on the nuclear medicine physics. Actually, that it is based on the chapter 6 of, this book. Actually, this is the table of contents of the chapter 6 of Physics in Nuclear Medicine book. That include the, the interaction of, charged particles with matter, and charged particle ranges, and passage of, high energy photons through matter, and the attenuation of, photon beams. But let me start with, the later part. I mean, I will, tell you about the photon interaction with the matter first, and then let me go back to the interaction of charged particle, such as alpha and beta, with surrounding matters. Okay. So actually, yeah. So because this is a very the basic lecture on the physics, so yeah, it can be boring. So if you have any question during my lecture, please let me know through the chatting box, or you can just ask me. Okay. Okay. So let me start with how photon interact with the atoms. Yeah. Here, the photon means usually the gamma ray in nuclear medicine and X-ray in radiology. Yeah, I mean that the photon that I'm mentioning is high energy photon, so that has higher energy than the visual light or the ultraviolet or something like that. So the photon mentioned here should have at least several kilo electron volt, and each range is several kilo electron volt to several mega electron volt. Okay. Yeah. Anyway, that you can just think the photon that I'm mentioning is gamma ray or X-ray or something like that. Yeah. Anyway, there are 4 different mechanisms how the photon gamma ray interact with other atoms. And these 4 mechanisms, the interaction mechanisms include Rayleigh or coherent scattering, and Compton scattering, photoelectric absorption, and pair production. So yeah, in my following slide, I will tell you about each of these 4 different mechanisms. Okay. The first, the interaction mechanism of high energy photon with matter that I'd like to tell you is Rayleigh or the coherent scattering. Yeah, actually, this Rayleigh or coherent scattering happen when instance high energy photon excite the total atom. So in this case, that the older electrons around the atom, I mean nucleus, oscillate in phase simultaneously. Then this electron, excited electron cloud immediately emit energy by emitting a photon of approximately the same energy but in a slightly different direction. So I mean that the actually instance photon is coming from this side to the nucleus, and after some interaction, this photon, the scattered photon, is released from the this nucleus. But if you compare the wavelengths of distant, instant, and scattered photons, their wavelengths are same as described here. So it means that the energy, so as you know, the energy of the photons, electromagnetic wave, is dependent on its wavelength or the frequency. It is determined by the wavelength. So because that they have same wavelength, it means they have the same energy. Okay, so you can see the during this interaction, no energy is changed before and after interaction based on interaction with Rayleigh scattering. So that is the most important point that you should remember in this slide. No change in the energy or the wavelength in spite of the change of the direction of a flight of high energy photons like that. They change direction, but no energy is changed. Okay. So actually, so it is very not easy to identify whether this scattering, happen or not. Why? Because no energy change is involved. So scattered photon, because scattered photon has the same energy as incident photon, it is hard to know whether this photon was scattered or not. So this is a very bad situation, and it is quite different from the Compton scattering that we will discuss later. Actually, that in Compton scattering, the energy is changed. So based on the energy, so we can say whether this is scattered photon or not. But the photons that underwent Rayleigh scattering has the same energy as before. So it is hard to say whether this was scattered or not. Okay. Unfortunately, this interaction mainly happens with very low energy photons. I mean that this interaction occurs with the high energy photons with energy between 15 to 30 kiloelectron. It is quite low. So you can remember that, the energy of photon that we typically use has a range of at least 80 kiloelectron volt or something like that. So actually that such a high energy photon with higher energy than the 30 kiloelectron volt usually do not undergo this Rayleigh scattering. So this is good news for us. Okay. So let me now tell you what is Compton scattering. Yeah, Compton scattering is quite similar as Rayleigh scattering, because the instance photon, the change its direction by the interaction with this metal. Yeah, but if you focus on their wavelength here, actually scattered photon has a longer wavelength than the instance photon, right? Lambda is wavelength here, and lambda 2 is longer than lambda 1, the wavelength of instance photon. Yeah, actually, that the longer wavelength means low energy. I mean that the low energy photons has a longer wavelength. So it means that some energy was lost during the disintegration. I mean that the scattered photon has lower energy than the instance photon, because this photon lost its energy during disintegration. Where did energy go? Yeah, actually, this energy was used to emit this Compton electron from the electron orbit, as you can see here. I mean that some part of the energy of instance photon was used to expel this Compton electron from the orbit like that. So this is quite makes sense. Some energy was used here, and actually this scattered photon has remaining energy, right? That is why this scattered photon has lower energy than instance photon. Yeah, actually, that then this Compton electron will have some kinetic energy. So that is, smaller than the energy difference between this scattered and instance photon, because some energy should be used to overcome the binding energy of this electron in this orbit, right? Yeah, and what's the energy of this Compton scatter electron? Yeah, actually, that it is not deterministic value. Actually, that the energy of this Compton electron is, variant depending on this angle of, diffraction. I mean, the energy of Compton electron is determined by the angle of, this diffraction. With, smaller angle, the Compton, the electron will have, low energy. And with the larger angle, the Compton scattered electron will higher energy. Because, this is, instance photon lose, more energy when this, angle of diffraction is large. Okay. So, actually, this equation describes the relationship between the energy of, this scattered photon and the, the angle of, diffraction. Okay. So actually, this equation show you with, higher angle of diffraction, the energy of, the lower the energy of this, scattered photons. E0 here is the energy of this instance photon. Actually, that this interaction is most likely occur between photons and outer shell electrons, because that the outer shell electron is easier to detach than the electrons on the the inner shells like that, because it has a lower binding energy. Yeah, anyway, as I told you, the scattered photon has a lower energy than instance photon. So based on this energy changing, so we can say whether this photon was scattered or not. Yeah, actually, so you can think about this situation. We measure some photons, gamma ray photons. So if each energy is the same as the energy of the primary photon, I mean that the energy of the photons coming from some radioisotope, we can say this was not scattered, Compton scatter. Yeah, actually, we know what's the energy of photon from some specific radioisotope, because that is deterministic value. For example, from the technetium 99M, 140 kilo electron volt gamma ray is coming only. So if measured energy is 140 kilo electron volt, we can say it was not scattered by the Compton scatter. Yeah, but the measured energy is lower than such a specific value. We can think it may be underwent on Compton scatter. For example, if it has a 100 kilo electron volt energy, it is very likely that it underwent Compton scatter. Do you have any question? Can you mute your microphone? I'm not sure where this sound is. Okay, good. Thank you. Yeah, so as I told you, the photon change energy, due to this Compton scattering. So this is why, that in the gamma camera and pan, we apply some energy window. I mean that we apply, for example, plus minus 10% energy window around primary photon peak of each radioisotope to reject these Compton scattered photons based on this energy information. So the Compton scattering is quite important. Yeah, what will happen if we do not, reject such a Compton scattered photons? Yeah, actually, that if photon scattered, it is very, yeah, actually, that this angle is quite random. So it is hard to, hard to say where was its origin of the emission. So these Compton scatter photons contribute to the images as a background noise. So that is why we should, remove these Compton scattered photons based on the energy window. Yeah, but unfortunately, the radiation measurement systems doesn't have sufficiently good energy window. So that is why energy resolution. So that is why it is impossible to totally eliminate exactly the scattered photon only based on the energy information. So that is why we perform some additional scatter correction, the method to remove some remaining scattered photons after applying the energy window around the primary photon. Yeah. Anyway, so yeah, this slide shows the the relationship between the scattering angle and ratio of energy between the incident photon and scattered photon. Okay? So as I told you, with higher angle, the larger angle, the photon lose more energy like that, right? So yeah, this is very important information. Yeah, but actually, that this Compton scatter angle does not distribute uniformly. I mean, actually, the possibility of for example 10 degree of scattering and 20 degree scattering is different. It is not uniform. Yeah, actually, this slide shows such a the probability of the scattering angles. So the x-axis is scattering angle, and y-axis is relative probability. So this slide actually, that this figure shows that it is more likely that the scattered angle, range between 30 to 120 or something like that. And this distribution also depends on the energy of instance photons. I mean, that the low energy photons has more uniform distribution, but with higher energy the photons, the smaller the scattering angle is more dominant. Okay. So actually, this means that the gamma camera single photon imaging, the scattered photon can have larger the scattering angles than PET application. So the scatter correction is quite important for the gamma camera or the spectral image. Okay. Actually, that I told you two different mechanisms so far. I mean that interaction mechanism, Rayleigh scattering and Compton scattering. And the third one that I'd like to tell you, I will tell you, is photoelectric absorption. Yeah, absorption is different from the scattering. The scattering means the change of the direction of flight, but the absorption means that the photon will be lost. Photon will disappear. So all of the energy that photon has will be absorbed by the atoms, surrounding matters. So there is no instance photon, but no scattered photon. Because all of this instance photon is absorbed by this atom. Then the absorbed energy is used, all of the absorbed energy is used to emit this photoelectron. Yeah, we call this guy photoelectron. Okay? So the energy of a photoelectron is the difference between the energy of instance photon and the binding energy, original binding energy of this electron. For example, if the instance photon has had 100 kilo electron volt, and the binding energy of electron in this shell was 34 kilo electron volt, the energy of photoelectron will be 66. It means 100 minus 34. So depending on the interactive electron, emitted electron, this photoelectron can have different energy, but it has some discrete value depending on the binding energy of each shell of some specific the atoms. So this is photoelectric absorption. The outcome of this interaction is only the electron and no scattered photons. We lose the photon. So this is the main mechanism of photon attenuation in addition to the compensation, because we lose photons in this interaction. Yeah, usually that after this photoelectric absorption happen, we can observe some characteristic X-rays like that. Yeah, I mean, if that the photoelectron is emitted from this shell, it makes some vacancy here. So as you know, if there is some vacancy of electron in the inner shell, actually that the upper shell electrons with higher energy is likely to occupy this vacancy of electron. It means that some electrons in the higher shells, electron shells, will move to these lower shells. Because that the inner shells has lower energy status. Electrons like low energy. And such a difference between this the electron shells will be emitted as a the characteristic X-ray. So I mean that if there was vacancy here created by this photoelectric absorption, and some electron from the the upper shell here was moved to here, so the difference of the energy is 20 9 kilo electron volt. So 29 kilo electron volt characteristic X-ray will be emitted after this photoelectric absorption. So this is the consequence of this photoelectric absorption. Okay. And what is pair production? The last mechanism that we should remember today. Yeah, actually, that this pair production only happens by high energy instance photons. They should have higher energy than 1.02 mega electron. Actually, that in this pair production, the energy of instance photon is converted into electron and positron. I mean that the energy is converted into the mass of material. So actually, this is some opposite phenomena of mutual annihilation. So as you know, in PAN, the mutual annihilation happens. I mean that when positron meet electron, their mass is converted into the energy of gamma ray. So 511 kilo electron volt gamma ray is emitted after this mutual annihilation, by the mutual annihilation. But this is very opposite to such mutual annihilation. I mean that the photon is coming and energy of photon is converted into the mass. And one of them is positron and the other is electron. Yeah, now I think you can. So you can see. So you know why the energy of instance photon should be higher than 1.02 mega electron volt. So that is the 2 times of 511 kilo electron volt. That is equivalent to the the last mass of this positron and electron. So to generate this particles, the energy should be higher than their equivalent energy as their last mass. Okay. Yeah. So, but fortunately, this pair production do not happen during the our imaging procedures, because that we usually use lower energy photons than 1 mega electron volt or something like that. Yeah, but in the therapy it can happen because that in the therapy we use we can use higher energy photons. Yeah, actually that yeah, one of the another consequence of this this pair production is to annihilate the photons. I mean that the positron generated by this instance photon undergo some mutual annihilation with other electrons, and the mass is again converted into the 511 kilo electron the gamma rays like that. Okay. Yeah, so I told you 4 different mechanisms of photon interaction with the atom. Yeah, it was Rayleigh scattering, Compton scattering, and photoelectric absorption and pair production. Yeah, so let me now move to the attenuation of photon. Yeah, actually that the attenuation means the removal of photon from a X-ray beam or gamma ray as it passes through some metals. And all of the interaction mechanisms that I told you can contribute to this attenuation of photons. I mean that we can lose the photons by the Compton scattering, or by the photoelectric absorption, or pair production, or something like that. Yeah. Anyway, so these attenuation photons can be described by this equation. Yeah, if the intensity of the incidence photon is I0, and this attenuator, the thickness of this attenuator is X, and the linear attenuation coefficient of this material is mu, then the intensity of the transmitted intensity, the beam, will equal to I0 multiplied by exponential minus mu multiplied by X. Yeah, actually, if you focus on this exponential term, so you can see, the higher attenuation will, happen with, the thicker attenuation material, and there will be, higher attenuation if it has, higher linear attenuation coefficient. Okay, and as I told you, all of these four mechanisms, Rayleigh, photoelectric absorption, Compton, pair production, contribute to this attenuation. But their dominancy would depend on the energy of photons. For example, as I told you, Rayleigh scattering only happen with very low energy photons. So if energy of the photon is higher than 30 kilo electron volt or something like that, the contribution of Rayleigh scattering will be small. So the important point that I'd like to tell you is their contribution depends on the energy of instance photon. And their dominance of contribution also depends on the material. Depending on this material, their dominance is changed. For example, with the material, material with a higher atomic number and the higher density, the photoelectric absorption is more dominant than Compton scattering. So that is why we use, for example, lead or tungsten for the radiation shielding, because they have high atomic number. Photoelectric absorption is more dominant than Compton scattering. So it means that they can totally block the radiation as a radiation shielding material. Anyway, let me show you. This figure first. Actually, this figure shows you such a different contribution of 4 different mechanisms on the photon attenuation, depending on the energy of instance photon. Yeah, actually, that so x-axis, the standard for the energy of instance photon, and y energy is attenuation coefficient. Yeah, with lower energy, so you can see here. The Rayleigh scattering, it has higher contribution, but its contribution drop quickly. And photoelectric absorption contribution also drops like that. But Compton scattering still contribute a lot. And if energy is higher than 1 mega electron volt, the pair production start to contribute like that. So this slide shows that within higher energy photons, the Compton scattering is more dominant than photoelectric absorption. For example, we use 511 kilo electron volt photons for past studies. For such a high energy photon, Compton scattering is more dominant than photoelectric absorption. So this is very interesting. Yeah, this slide show the such a relative importance of 3 major types of gamma ray interaction: photoelectric absorption, Compton scattering, and pair production, depending on the energy. As I told you, with low energy photon, photoelectric absorption is dominant, but the 511 for past studies, Compton effect is more dominant, and with higher energy, the pair production is more dominant. So this is very interesting. So let me now move to go back to the how we can measure the attenuation coefficient. Actually, that measuring the attenuation coefficient is quite important for the attenuation correction of nuclear medicine images. Yeah, if this attenuation is not corrected, actually it is impossible to acquire some uniform distribution for the uniform radioactivity distribution. So the attenuation correction is quite important for achieving the quantitative accuracy of nuclear medicine images. Yeah, there are 2 different ways of measuring the linear attenuation coefficient of some materials. Yeah, actually, that if you compare these 2 setups for attenuation coefficient measurement, so there is radiation source here, and these are the attenuation material, and there is a detector to measure this radiation and counter. Yeah, and there are 2 different ways of measurement. The the upper one is so-called broad beam geometry, and the lower one is narrow beam geometry. Yeah, in the broad beam geometry, only the detector is collimated with some shielding materials like that. Yeah, but in the narrow beam geometry, both of the detector and source are the collimated like that. Yeah, if you compare this broad beam and narrow beam geometry, what do you think? Which do you think will have higher attenuation coefficient, more attenuation? Yeah, actually, that the narrow beam geometry would yield higher attenuation coefficient. I mean that the higher attenuation, because that in broad beam geometry, some scattered photons can come into the detectors like that, because the source is not collimated. So depending on the which geometry that we use, attenuation coefficient will be changing. Okay. So in the nuclear medicine, we use both of broad beam and narrow beam geometry, depending on the situation and depending on the correction algorithms. Yeah, if we just want to correct attenuation, it is better to use narrow beam geometry. But if we want, both of scattering and attenuation together, we can use, narrowing geometry attenuation coefficient. Okay. Yeah, this slide shows the energy dependency over attenuation. Yeah, actually, that how much attenuated the photon depends on the energy of photons. Think about that. So which will be more attenuated? Higher energy photons or lower energy photons? Actually, that with higher energy, the photon can penetrate the materials easily. I mean that with low energy, it is more likely that photon will be absorbed by the materials because energy is too low. So this is why this x-axis here is the depth of source, and y-axis is the percentage of transmitted photons. So you can see the lower energy photons has the smaller percentage of transmitted photons. It means that the more photons were lost by the attenuation in the same depth of source radiations. Okay. Yeah, if you compare the Psyllium spec and technetium 99 spec, actually that the Psyllium spec, myocardial spec, the sulfur more significant the attenuation because it has lower energy than technetium 99M. So this slide show why such a thing happened. Yeah, this slide shows the dependence of attenuation on the attenuating material. Yeah, as I told you, some dense and the material with the higher density and higher atomic number, the attenuated radiation, the better attenuated radiation. So the bone is better attenuated than water, and water is better attenuated than love. So this is why the percentage of transmitted photons is lower with bone rather than water or lung in the same the source steps like this. Okay. I explained to you this slide before and this one as well. Okay. Yeah, so so far I told you the main mechanism of photon interaction with the atom, and told you how the attenuation coefficient of the materials are determined by such 4 different mechanisms, and what's the dominance of such mechanisms depending on the energy. So let me now move to the interaction of charged particles with metals. Yeah, actually that the mechanism of the interaction of charged particles are very different from the ionizing photons. Yeah, because that the charged particle, if you compare the photon and charged particle, they have quite different characteristics. Photon doesn't have any mass. It only has the wavelength, and it doesn't have any charge, plus or minus. Yeah, but the particles, alpha and beta rays, has significant mass. Especially alpha is very heavier than the electron, And both of alpha and beta has electric charges. Alpha has plus 2 charge, and beta has -1 minus charge. So this is why their behavior is different from the photons. So now let me tell you how they interact with the metals. Yeah, actually that there are many different charged particles. So as I told you, the alpha particles, such as alpha particles and proton, positron, electron, and beta particle, all of them are charged particles. There is also uncharged particle, such as neutron. But the neutron is not widely used for nuclear medicine. So let me just focus on the charged particles here. Yeah, two main mechanisms of charged particles are excitation and ionization. I mean that the charged particles induce the excitation of the electrons on the the electron orbit to excited states in atoms, molecules, or a crystal. So they make the electrons on some atoms excited by transfer their energy or interact with them. And these charged particles can also lead to the ionization of the atom when it removes such electrons from the atom or molecule. Actually, that this is more active interaction mechanism than the excitation. Actually, that it removes electrons totally from the atom or molecules by its flow course or something. Yeah, because as I told you, charged particle has electric charge. So there is some Coulomb force between the charged particles and orbital electrons. So such a Coulomb force is used to excite the electrons or induce the ionization of the electrons, orbital electrons, molecules. Yeah, look at this. This slide shows how charged particle induce such an excitation, or first excitation of the electrons, orbital electrons. For example, that there are some positive charged particle like alpha ray or proton is coming from here, and it goes through the the surrounding the next to the atoms like that. Then due to it's very the positive Coulomb force, the electron in the inner shell can move to the outer shell like that. So each energy is elevated from lower status to the higher state. I mean that this atom is excited by this charged particle. So actually this atom has higher energy than before due to this excitation. And what will happen after this excitation occurs? Yeah, actually that if it is excited, this electron is excited, it generates some vacancy here. So some electrons in the higher shell, upper shell, will move to the this lower shell. Then either emit some electromagnetic wave or some OJ electrons. Yeah, as I told you, if there is a vacancy here, actually that the characteristic X-ray can be generated But this energy can be also used to expel, emit some orbital electrons. And we call this orbital electron the OJ electron. So in summary, two different, the consequence happens. I mean that the emission of, characteristic X-ray, emission of some electromagnetic wave that has the same energy, same energy as, the energy difference between these two different, electron shells. But this energy can be used to emit some orbital electrons. And this emitted orbital electrons by this excitation is called OJ electron. Okay, so yeah, so actually, this slide shows what is the OJ electron. OJ electron. So I mean that the electron emitted instead of characteristic X-ray. Okay, and this slide shows what is the characteristic X-ray. In terms of the the energy, the diagram. Okay. Yeah. Let me now move to ionization. As I told you, there are two different mechanisms: excitation or ionization. And ionization means, such a Coulomb force used, or the charged particle was used to totally, eliminate electron from the orbit of, some specific atom or molecule. Okay. So of course, that this mechanism occurs when the transport energy exceeds the binding energy of electron, like that. Okay. And this electron is ejected from the atom. And sometimes this ejected electron can behave as a secondary electron. I mean that this electron can be another ionizing radiation if it has sufficiently high energy, like beta ray or something like that. Yeah, imagine that this emitted electron has a high kinetic energy, high speed. It has sufficiently high energy to generate another ionization. It can happen. So we call this secondary electron that lead to such a cascading ionization, the delta rays. Delta ray is not common in the world, but we call this secondary electron delta rays. And as you can imagine, this secondary delta rays can lead to result in another ionization if it still has higher energy, high kinetic energy. So this kind of phenomena can occur in cascading rays. Okay. Yeah. Let me now tell you some some terminologies that define the number of primary and secondary ion pairs produced by the discharged particles. Yeah, actually, that the specific ionization is the number of primary and secondary ion pairs produced per unit length of charged particles pair passed. So this is a kind of measure how much the instance charged particle makes some ionization. So it is a measure of some dose delivery, energy delivery of charged particle to the surrounding materials. Okay. Yeah. Yeah. If we know that the charged particle, should, yeah, actually charged, it should have higher specific ionization if this charged particle can be effectively used for therapeutic purpose. Yeah. Anyway, this specific ionization increase with the electrical charge of particle. I mean that the +2 is better than +1, and this specific ionization decrease with the instance particles velocity. This is interesting. It means that within a lower velocity, it generates larger number of ion pairs. It's very interesting. We can simply think, the faster charged particles would have high energy, so it is more likely to generate larger number of ion pairs. But these slides tell you particles with a lower velocity generate larger number of ion pairs. So this is because that if the particle is too fast, there is no chance of interaction between the particles and the atoms because it is too fast. It goes away before it interacts with something. But the particle is slow. There is more chance to interact with surrounding atoms because it remains some point longer than the faster charged particles. Very interesting. Yeah. Anyway, the specific ionization decreases with the instance velocities particles velocity. And typical value for alpha particle is as high as 7,000 ion pair per millimeter in air, and electrons should has the smaller value that range between 50 to 100 electron pair per centimeter. Okay, the alpha is much stronger than electrons in terms of the specific ionization. Okay. I think you have heard about the Bragg pin. Yeah, actually, that the Bragg pin is such a thing. Actually, that this x-axis is the distance from the entrance point of the instance charged particles like alpha ray or something like that, and y-axis is the specific ionization. I mean the ion pairs per millimeter. Yeah, actually that this the specific ionization increase like that, but it leads to some maximum value and specific ionization drop quickly. So think about that. Actually, that the alpha particle was generated here, but it lost, the maximum energy. It lost energy, the maximally here, not its original position. So this is because that the alpha particle, when alpha particle was generated from the some nucleus, its energy is too high. It is too fast. So it is more likely to generate ionization. There is a smaller chance to generate ionization. Interaction probability is low. So that is why, as the alpha particle lose its energy and speed decrease, the specific ionization increase because velocity is slower than before. And slow and slow, and when it almost starts, it yields, the maximum ionization pairs like that. Then lose all of the energy here and it starts. So this is why some ionization peak, is observed, far from the, the original, the position where the charged particle was generated. Actually, this is very interesting, the phenomenon. And actually, that this Bragg peak, the principle, is also used in the external charged particle therapy, like the proton beam therapy or carbon beam therapy or something like that. Yeah, as you can, actually, that if we think about this, if we use the proton beam as a the external radiation beam, and actually think about, so this is the surface of your skin, the skin of the patient, and there is a tumor here. Then, and if we the modulate the energy of the proton, so we can make this maximum peak occur at the position of the tumor like that. So that is why in the proton therapy we can say some normal tissues located here and deliver maximum energy only to the tumors like that, using this Bragg peak principle. So this is a very, very interesting phenomenon. Okay. Yeah. This slide show the charged particle tracks. Yeah, actually that the alpha and beta ray has different the pattern of the particle tracks, because that the alpha is very strong. The path and the length they are same, but the electron has a longer path. The sum of all of these lines that is longer than range of this electron. The range is the distance from here to here. Okay, so actually they have different patterns. Okay, linear energy transfer (LET) is also very common term, very common term used in the dosimetry for charged particles. Yeah, actually, the definition of the linear energy transfer is the amount of energy deposited per unit path length. So with the higher LET, we can expect better therapeutic effect. And this LET is a product of specific ionization and average energy deposited per ion pair. Okay. Alpha and proton has higher LET, and electron and gamma has lower LET. And I'm sorry that I used some Korean here, but I wanted to tell you that OJ electron has higher LET than beta, because the OJ electron usually has lower initial kinetic energy. OJ electron is slower than beta ray usually. So some therapeutic radioisotopes based on the emitting the OJ electron is more effective than the beta particle, beta emitters. in terms of therapeutic effect. Okay. The scattering also happen in charged particles, of course. And the Bremsstrahlung X-ray is the result, one of the consequence of such a scattering of charged particles. Yeah. So actually, that the electron, for example, the electron, when electron change each direction like that, scattered, the electron will lose some kinetic energy due to this scattering, and such energy is used to generate Bremsstrahlung X-ray. Yeah, actually, that this Bremsstrahlung X-ray is used for X-ray tube. I mean that the X-ray generator, the majority of the X-ray plug that we use for X-ray examination is this Bremsstrahlung X-ray, the generate emitted from the X-ray generator. Yeah. So yeah, let me sum up my lecture today. So I told you some interaction mechanisms of the photons with matters in my first part, and in the second part I told you how the charged particle interact with matters. So in summary, for the photons in the first part, I emphasized there are four different mechanisms of interaction. They are Rayleigh scattering, Compton scattering, photoelectric absorption, and pair corruption. And I also emphasized that the dominancy of these mechanisms are different depending on the energy and the materials. In the second part, charged particle interactive with matters, and it leads to the excitation or the ionization. Okay, and there was two important terminologies: the static ionization and the linear energy transfer. Okay, alpha has higher linear energy transfer than beta, and OJ electron has higher linear energy transfer than beta as well. So the therapeutic effect is highest for alpha, and next is OJ electron, and lowest is beta. Okay. So this is the end of my presentation. So do you have any question or the comment about what I told you today?
Professor, I have one question regarding the attenuation difference. And you have mentioned about broad and narrow beam. Could you briefly explain, if it's possible, again for that part? So you mean the attenuation coefficient is different for?
조금 잘 안 들리는데 조금만 크게 말씀 주시겠어요?
제가 혹시 네로 빔이랑 그 브로드 빔 attenuation correction 관련된 부분 혹시 한 번만 더 설명.
Yeah, Professor So asked me to repeat the explanation of this slide. Yeah, so as I told you, there are two different ways of the measurement of attenuation coefficient. Yeah, I mean that each material has two different linear attenuation coefficient values. Yeah, one of them is measured based on this broad beam geometry, and another linear attention coefficient value measured based on this narrow beam geometry. So they have different values. As I told you, the narrow beam geometry lead to the lower measured count. So it will the attention coefficient the measured based on this narrow beam geometry will has lower values. So yeah, so look at this. So this slide shows broad beam geometry, right? So only the detector is collimated, and there is no collimation for radiation source. So actually, because that the source is not collimated, actually the radiation will be irradiated to the everywhere in the alternative materials, and some of the scattered photons can enter the detectors in this way. So that is why the higher count is observed in comparison with this the narrow beam geometry. Actually, that in the narrow beam geometry, the beam is coming only in this direction. So the smaller number of photons are coming into the attenuation materials, and scattered photons cannot reach to the detectors like that. So the smaller number of photons is observed here. Okay. So yeah, so the higher count is measured. The higher count is measured. So lower effective attenuation coefficient will be the estimate if this measurement was done based on the broad beam geometry. Okay. And yeah. So this is narrow beam geometry. So we can say actually that the narrow beam geometry the reflect some pure attenuation. Yeah, but the broad beam geometry linear attenuation coefficient will reflect scattered photons as well. So yeah, so this is why I told you if we want to remove the effect of scatter together with attenuation, so we can use broad beam geometry.
So if we do the scatter correction, it will be similar as the narrow beam geometry, or is it?
Yeah, so yeah, if we perform some scatter correction, it is usually recommended the use of narrow beam geometry attenuation coefficient is recommended. Yeah, but if we do not correct scatter, the broad beam geometry, the linear attenuation coefficient based on the broad beam geometry is more efficient.
Thank you very much.
So do you have another question? Yeah, next time that I will talk about the radiation measurement as I told you. So based on what I told, what I explained today. Okay. If you don't have any other questions or comments, shall we close here? Finish here.
Yeah, and I will like to inform everyone that as you all know, we are every time uploading this materials, and also within a week, the recorded lecture will be uploaded in the YouTube. So I think you can review, and because Professor Jason Lee will deliver us the lecture next week again, you can review and make up some questions, and we can discuss it next week again. Okay, then thank you very much, Professor Lee.
Thank you. Bye-bye.